Okay. So, any doubt? No, right? Any explanation is required? If there is no explanation required, let us move forward. Okay. All right. So, somebody is saying unable to. Okay. Santrupti, can you tell me which part I have to revise? You can unmute yourself or you can put it in a chat. Okay. You mean to say strain softening and strain hardening? Okay. Okay. All right. So then I will revise it and I will go to next topic. Okay. So let me go to full screen mode. All right. I'm finding a bit difficult today. Okay, no problem. I think now it is fine. Okay, all right. Now it is came for to full screen. Okay, so there is no much things we are going to discuss because I already told it is a very wide topic. So we are going to see only uh, gist of that. So only qualitative discussion. So we have already seen the plot of stress strain curve. Okay, so this is the sorry. Mm, So this linear region is a elastic region, elastic region. Okay, so this linear region is a elastic region. Okay, right? So elastic region up to this point. Okay, that is yield point. You can see up to yield point, it is linear. So whatever the curve we have seen after yield point, it is becomes non-linear and go to ultimate tensile strength, then decreases and breaks. This is a breaking point. This is what exactly we have seen. But in some of the material, you can see that after yield point, it will bend. After yield point, it will bend like this. Then again it will increase and go to maximum. Then it will go like this. Okay. So important point what you have to note is why that after yield point in the plastic region, it's not in the elastic region, in the plastic region it decreases. So what exactly meaning? So it material behaves like it is a soft material. Okay, it behaves like a soft material. It behaves like a soft material. Okay. So that is the reason. That's the reason why it decreases. It decreases. All right. So that's known as strain softening. In the same manner, just now we have seen in the whatever we have in the general case. In the general case, so what exactly happens after yield point increases, go to maximum, then decreases. So this is what exactly. I think I hope you can see that. All of you please mute yourself. Who is that? Don't unmute. Keep muted. Okay. All right. So what exactly you can see is, so you get a maximum up to this point, up to this point. So you find increases to this point, then it decreases, correct? So this is an important point. So ultimate tensile strength, but here this is a plastic region. This is a plastic region, non-linear. So what exactly happens is, to produce, you can see it is non-linear. Not only that, more amount of stress is required to produce strain. So that means materials behaves like a harder and harder. So best example for this is, if you have a piece of wire, if you want to cut it, if you want to mm, break into two pieces, if you don't have a cutting plier or some tool, then how you cut it? Wire, you bend it, right? You bend up and down, correct? You bend up and down, something like this. So you bend like this, and then you do like this, correct? Up and down. So you bend the wire up and down. The important point is, this is a important point, the point at which you want to break. Okay, so you move wire up and down. So then what exactly, one thing is, at this point if wire is get heated, but important point is, if you recall your experience, after 2-3 times bending, so you find it next time it is very difficult to bend. It's very difficult to bend. Mute yourself. Mute yourself. So you find it difficult to bend. Why you find it difficult to bend? Because material becomes harder and harder. That is because of the strain hardening. It's because of the strain hardening. Why exactly material shows strain hardening? Let us try to understand that. So just let us go to, so if you see the material, okay, just whatever I have done yesterday, just recall that. So in the material, you see the atomic arrangement, okay, atomic arrangement is like this. This is a systematic arrangement. One atom, next atom, next atom. So there is a systematic arrangement you can see here. A regular arrangement of atom. Sorry, I have covered this part. All right. So, okay, up to this part. Okay. So there is a regular arrangement of atom. Whereas here you can see atoms are missing. Atom is missing. Here you are supposed to have another atom, but it is missing. At this point you should have another atom. At this point, you should have another atom. So that is missing. So therefore, but bond length increases. That bond is strained. So therefore, you can see. So there is a strain. Bond length is more. It's unstable state. The same manner here you can see one extra atom. Because of that, this area get disturbed. Here you can see extra impurity because of this area is disturbed. Here also due to impurity, this area is getting disturbed. This is due to impurity. So see here again one atom is missing. So you can see here the different way. So here again, what you can see, here one layer is missing, here like this in between, in this region. Carefully if you see, in this region atoms are missing. Okay, so like this material is not a perfect one, so there will be number of atoms are missing. Okay, so because of this what happens when you apply the stress, let us go to next slide. This is what exactly first one I have shown. This is a perfect. Okay, this is a perfect material. There is no, what is that? Um, Impurity or imperfection. Okay, there is no impurity or imperfection. Somebody has unmuted. Please mute yourself. Who is that? Because of that background noise is coming. Please mute yourself. Muted? Okay. I hope you have muted. Alright. So now, what exactly happens? Just see here. When you apply the force, okay, you apply the force. Now, before applying the force, this is no stress. Now you apply force. Then what exactly happens? Upper side deforms, bottom is stable. Then, so atom starts slipping. That's what exactly happening here. Slipping. If you remove the force, this is the status. So this deformation is permanent. This deformation is permanent deformation, plastic deformation. It will not regain. Only that orientation, inclination change, that is regained. Okay, this is what exactly ideal. Okay, but when there is a defect or impurity, then it is very difficult to slip. It is find it difficult to slip. So that is what exactly happens. Strain hardening. This is what exactly the situation. Overall situation. Okay. So that is why material get strain hardened. Okay. Is it fine? You can reply. Yes. Yes. Okay. All right. I think it's clear. Next, a small topic, fracture or fatigue. Okay. So we have seen what is that? The stress strain curve. Okay. The stress strain curve we have seen fracture point, correct? So in the stress strain curve, so this curve, okay, this linear region, then non-linear breaking. This is a fracture point. Okay. But important point is Uh, this is when you apply force, continuously apply more than the elastic limit. If you apply, this is what exactly happens. But in reality, in practical situation, it is different. Fracture or fatigue is different. When a material or machine or a part of the automobile is repeatedly used. So you might have seen, what is that? Um, uh, Bike cable, brake cable breaks, or different parts of the automobile brakes. Okay, so suddenly it get broken. Suddenly it get broken. Why it is so? Why it is so? So repeatedly the material is get stressed, loaded and unloaded. So then what exactly happens is, if you take a material, let us say, for understanding, let me take, all right, a block. Okay, all right. So this is a block of material. So when you subject this material for continuous um, continuous stress, then what exactly happens is, inside the material small crack develops. Slowly this crack becomes bigger, bigger and bigger, and it propagates, and finally it reaches the surface. Then material breaks into two pieces. So from this point material is broken. So now material becomes two pieces. So this is known as fracture or fatigue. It's a fatigue fracture. This is known as fatigue. Okay. So Mayur is asking something, sir, does it work same as in honeycomb structure? I didn't get you, Mayur. What exactly you wanted to tell? For which one you are asking? You can unmute yourself and speak, that's better. You are talking about previous one, strain hardening. No, no, it's not. What is your question? Yeah, whatever may be the structure, it will work. Okay, whatever may be the structure, whether it is honeycomb structure or whatever may be the structure, it will work. Okay. All right. So this what exactly fatigue. So not much discussion about this topic. Let us move to the next topic. Important topic. So we will move on to bending of beams. First, let us try to understand what exactly beams. So beams are bar of uniform cross section whose length is very much larger than thickness. So this is one beam. So one side of the beam is rigidly supported, other end is not supported. So this is one beam. So such beam is fixed at one end and loaded at the other end. The beam is bent. You can bend the beam. That is, bending is known as bending of beam. So you can fix at one end or either end you can fix, no problem. This end you can fix. That's a case of bridge. Bridge is a best example. Both end is supported. Middle is loaded. So then also beam will bend. Okay, beam will bend. So whenever it's subjected to load, beam is bent. What are the things happens in the beam? Let us try to understand. What exactly happens? Suppose say a beam gets subjected to load uniformly. So let us say both end of the beam is supported, middle, at the middle you are applying the force, then it bends uh, like this, whatever second picture. Okay. So what exactly happens? Upper surface of the beam is stretched. Length of the upper surface increases, whereas lower surface get compressed. Length of the lower surface decreases. So that means extension is a maximum at upper surface. Correct? So what you can assume is beam is made up of number of layers. Let us say call it as a filament. Let us call it as filament. So there are number of filaments. What exactly happens? So upper filament has got maximum extension. Okay. Then and compression. So you can see is, so this is maximum extension reduced. Here there is no change in dimension. Whatever initial dimension, same dimension is here. Okay. Next, as you come down, dimension decreases. That means material, filament get compressed. Filament get compressed. Lower filaments get compressed, which is neither, that is a middle one. So this is known as neutral filament. Okay, which is neither get extended or neither get uh, contract nor get contract. That is known as neutral filament. Neutral filament. Below this, again the layers get contracted or compressed. So as you come down, the lowermost filament have compressed for the highest extent. The highest extent. Okay. If bending is uniform, okay, then this longitudinal filament bend like a circular arcs. Okay. So all are like a arc, circular arc. So bends like, if it is uniform, then it is known as it bend like a circular arc. Is it okay so far? Clear? The first point is, what is beam? Beam is a uniform cross section, a bar of uniform cross section whose length is larger than thickness. That is very, very important. It should have a uniform cross section. That is important. Its thickness or radius. Please don't think beam means only rectangular cross section. Even circular cross section is also possible, but it is called as cantilever. Okay, circular cross section beam is called as cantilever. Okay, even this is also known as cantilever only. Cantilever means one end is supported, other end is not supported. Okay, circular cross section beam is possible, rectangular cross section beam is possible. Okay, shall we go ahead? Clear? Is it clear? No reply? Okay, okay. All right. All right. So let us move forward. So what are the applications of beam? To understand the application of beam, you should understand what are the different types of beam. Okay. So there are different types of beam. one end is supported, other end is not supported. That is known as cantilever. Cantilever. Then both end of the beam is supported. That is known as simply supported beam. Okay, simply supported beam. Then support is not given at the end of the beam. Two supports are given. Two supports are given, but there will be a overhanging of beam. This is known as overhanging beam. But of course, if you consider only this portion, this is a cantilever. This is a cantilever. Okay. But if you consider complete beam, this is overhanging beam. Similarly, both ends of the beam is supported. Not only that, in between also it is supported. This is like a bridge. This is a case of bridge. Okay. But actually, actual case of the bridge is this. Actual case of the bridge is this. Simply supported, because the bridge is not like this. It's not a continuous beam. It is a pieces of beam. Pieces of beam is supported at the ends. In between middle there is no support. So this type is known as continuous beam. Okay, continuous beam. That means in all these three cases, beam is supported from the bottom. Okay, simply supported, overhanging, continuous support beam. Okay, then another type is fixed ended. So that means beam is supported from the side, not from the bottom, not from the, so both end of the beam is supported. Okay, so that is known as fixed ended. Fixed ended. Similarly, one more type is cantilever simply supported. One end is supported from the side, another end is supported from the bottom. Cantilever simply supported. Okay, this is also possible. So all these are depending on which type of the beam, you can use it for different application. Cantilever and beams have plenty of application. So in your daily life, you can see all this. Okay, cantilever you can see in the building, simply supported you can see in the bridge. This is a bridge, case of bridge. Okay, this you can see in the buildings. This also you can see in the buildings. Okay, even in the vehicle also you can see this, both overhanging and continuous. uh, Instead of this, the wheel, whatever support is, wheel is a support. This is a multi-axle for support. This is a multi-axle vehicle. This is two axle. Okay, so this is again in the building, this is possible. This is also possible in the building as well. So this cantilever is possible in the case of in electronics and communication. You can use the cantilevers. So something like here there are given. Okay, some example I have given. Beams are integral part of civil engineering structure, bridge, dam, multi-storied buildings, measuring device. This is an electronics application, that is in tunneling microscope. Tunneling microscope, cantilevers are used. Automobile frames, aircraft component, machine frames. So all these are again beams. So these are designated to withstand heavy load. Cantilever beam, simple support beam, connecting beam. So that is then roller beam. Roller beam. Roller beam, that's what exactly I have talked about. So if you put wheel for this continuous support beam, or yes, or overhanging beam, then it is a roller beam. So that is observed in the case of vehicles, heavy structures you want to move. Okay, all right, is it clear? Next, Let us see bending. So you have the beam, now you are using for application, so beam undergoing bending. Then what are the possibility? Okay, let's consider uniformly bent. A beam is bent uniformly. What are the things happening? So of course I just forgot to put ABCD. Let us say this is A, B, C, D. Okay, so fixed beam. Okay, so AD is a fixed end, so that means, so for simplicity let us take, okay, here itself for explanation purpose, this end is A, this end is B, this end is C, this end is D. So what it says, AD is a fixed end. Yes, AD is fixed end because it is fixed to support. This end is fixed. So this end is a loading end. Okay. EF is a neutral axis. So if you take all the filaments in the beam, central filament will not undergo compression or extension. Compression or extension. So that is known as neutral axis. EF is known as neutral axis. Okay. All right. All right. So that's what exactly. Now, let us say W is the force acting. Okay. So whenever I mean, whenever W, okay, W, you can say it as mass into gravitational force, weight is acting. So whenever subjected to force, there will be always a beam will have a restoring force in the opposite direction. Okay, the opposite direction. Reactional force, which is acting upward. So let us say P dash, P dash representation that is in the middle. So at this point you can see when you bend the beam, one set of force is acting in this direction, another set of force is acting in this direction. So two set of force is acting. So two opposite forces are acting. Two opposite forces are acting. So that means opposite force acting means which forms a couple. Which forms a couple. Okay. And the moment of this couple is known as bending moment. Moment of this couple is known as bending moment. That is, moment of this couple is known as bending moment. Okay. All right. So let us consider beam is bent in the form of circular arc. Okay. Beam is bent in the form of circular arc. So this what exactly? So that means, so which forms an angle theta at the center of curvature. So let us say O is a center of curvature. Let us consider a section P, Q, S, T. Okay, let us consider a section out of that curvature. P, Q, S, T. Let us consider a section. All right. So now EF is the neutral axis, that is central. Above this there is a extension, below this there is a compression. So that means which is under a above and below. They are uh, giving a tension to layer EF, neutral axis. Even though it is not undergoing an extension or compression, still it is under the pull. Okay. All right. You follow this up to this point. It's clear. Then we'll see small derivation. Yes. Clear. Okay. Let's go to next slide. Okay. Okay, all right. I just forgot to put the animation. No problem. So, now consider same image I wrote in a small image I put. So, now let us consider one more arc DC. Okay, one more arc DC, which is slightly above the neutral filament. So, distance between this is, let us say, small r is the distance between neutral filament and another filament, and capital R is the radius of the arc formed by the EF. Capital R is the radius of the arc formed by the neutral filament or neutral axis, okay, which is forms an angle theta. So these things are shown in the figure. The same manner, DC is another filament. DC is another filament. So which is slightly above. So that distance, let us say small r, slightly above the neutral surface. Then you can write EF is equal to, that is filament, neutral filament is equal to R into theta. Because theta is a small angle, please remember, even though I have shown very big. So small angle, okay, right? Then what about DC? If EF is R theta, then automatically DC is equal to radius is increased by R plus R. Theta remains same, theta will not change. So therefore DC is equal to R plus R theta. So therefore increase in the length of the filament can be written as DC minus EF. DC is extended filament, extension, because higher upper filament undergoes extension. So therefore DC minus EF. What is DC? DC is nothing but R plus R into theta minus capital R into theta. So therefore you are left with small r theta. So therefore you can write the strain. What is strain? Definition. Change in length to the original length. Change in length to the original length. What is the change in length? Just now you have found out what is the change in length. That is r theta. Write that small r theta divided by original length. What was original length? That was EF. EF was the original length, that is capital R theta. Okay. So therefore theta theta will get cancelled. You are left with R by R, small r by capital R. Okay. All right. What is Young's modulus definition? As per definition, Young's modulus is equal to Y is equal to stress by strain. So therefore you can write stress as Young's modulus into strain, that is Y into strain. What is the strain in the previous slide? Yes, what is the strain? Strain is R by R. So therefore, Y into R by R. Okay. Let us consider filament with the area A. Okay. Consider the filament with area A lying at distance R from the neutral axis EF. So that is we are talking about, just let me take that previous slide. So let me copy this and put it in next slide, so for explanation purpose. All right. So what you can see, what is you are talking about? Consider a filament with the area A. So you are talking about a DC filament, this filament. Okay. So that is having area A at a distance R, small r, yes, that's what exactly, from the neutral axis. Then F, capital F, is a force on the area A. What is stress? Stress is called as force per unit area or force per area. Okay. So therefore, force can be written as rewriting stress is equal to force per area. Correct? As per definition. As per definition, stress is equal to F by A. Correct? Alright. F by A. So, if you want to force, what do you have to do? Take this A to the side. Correct? F is equal to stress into area. That's what exactly done here. That's what exactly done here. So force on area A is equal to stress into area. What is stress? Just now we have found out. That is Y into R by R. What is area? Area already just now we have defined. That is A. So therefore Y into R by R into A. That is force acting on the area. Okay. So moment of the force about the neutral axis, moment of the force about the neutral axis can be defined as F into, this is into, F into distance of filament from neutral axis. Force into distance of filament from the neutral axis. Which filament you are looking for? You are looking for a filament which is at a distance of R from the neutral axis. We are talking about DC filament, okay, upper filament. So therefore, F, force on the filament. What is force on the filament? That is F. Okay. Alright, F is given by, what is F? Just now we have found out F is nothing but Y into R by R into A. Okay, so that's what exactly here we have substituted force F Y into R by R into A into distance of filament from the neutral axis. Just now we have defined what is the distance. Distance is small r. So therefore you get Y into R square into A divided by capital R. Okay. Hence, moment of the force acting on the entire beam. So this is moment of the force about the neutral axis EF. This is on one filament you are talking about. You are talking about one filament. The whole beam, which is made up of number of filament. Okay. So therefore, moment of the force acting on the entire beam, if you want, you sum it. Take a sum of the moment of the force about neutral axis for all the filament, Okay, so therefore what you get if you sum it, so what will change? That is r. Okay, its parameter will change, so therefore you will get y into summation of r square a divided by r, or that a r can be written in terms of radius of gyration. Okay, radius of the gyration. Okay, so that is, you can write it as y into a into k square divided by r. Okay, where a, small a, is the area of the beam. Okay, area of the beam, and k is the radius of the gyration. K is the radius of the gyration. So you can simply substitute ak square can be, it's called as geometrical moment of inertia. So it is can be replaced by ig. Ak square can be replaced with ig. So therefore, what do you get? You will get expression as, if you replace that, so that is known as bending moment of beam or moment of the force is equal to y into ig by r. Y into ig by r. Okay. All right. If the, so then we can think of different cross section for the beam. There are two cross section are possible. One is a rectangular cross section, another one is circular cross section. If it is a rectangular cross section, then ig ak square is nothing but bd cube by 12, bd cube by 12. So therefore bending moment for rectangular beam, bending moment for rectangular beam is y bd cube 12r. Okay, 12r. Similarly, okay, of course, in that b is the breadth, d is the thickness of the rectangular cross section. Okay. Similarly, for the circular cross section, what happens? Let us see. For the circular cross section, ig is equal to ak square is equal to pi x to the power 4, where x is the radius of the circular cross section. Where x is the radius of the circular cross section. So therefore, bending moment can be written as pi into y into x to the power 4, 4r, 4r, where x is the radius of circular cross section. Okay, this is what exactly bending moment of the beam. Okay, all right. So I think I can stop here. I will go for attendance poll. Many people have left. I will give only 1 minute for recording attendance. Okay, within 1 minute you have to give your answer. Okay, let me open the poll. Yes, record your attendance. With attendance, I am going to conclude today's class. So, any doubt? Any doubt? If you want to clarify, any clarification is required. If no clarification is required, as soon as attendance poll is over, we are going to wind off the class. It's clear? Okay, good. So that means after giving attendance poll, you can leave the class. Thank you for attending the class. We will see you in the next class. Yes, you can leave the meeting. Once you record the polling, you can leave the meeting. Okay, I'll stop recording.